All right, so we start. So we were talking of dangerous optimism and pessimism. अंदर आ जाओ भाई. So we were talking about dangerous optimism and pessimism. Now, how do these things fit in this case? How do these two things fit in what we are doing here? So give me answers in terms of minimax, expectimax. So this is actually minimax, right? Your adversary is, so your opponent is adversarial, right? So a perfect opponent, and we assume that it is a expectimax. So when the problem is actually minimax, we start making a expectimax tree for it. In this case, when the problem is actually, so when we should use expectimax, but we are actually using minimax. Okay. Now this is again a very nice thing. So let me see if there is a way to run this. So there is a very nice demo for this. I am not sure if they have it here. So what is this case? Minimax Pacman, what does it mean? Pacman is going to assume that the ghosts are adversarial, and let's say they actually are. So in that case what happens? Pacman assumed ghosts are adversarial, they are, and Pacman won 5 out of 5 times, which is fine. Okay. What happened here? What happened in this case? Pacman is Expectimax. What is Pacman thinking? What is Pacman thinking in this case? That ghosts are not adversary, they are chances. Okay. In that case, won just 1 out of 5, and maybe even this one was just a matter of chance. Okay. What happens in this case now? When Pacman thinks that the ghosts are random and they are actually random, you still won 5 out of 5. What happens in this case? This is also fine, because if you assume that things are random, so if when you assume that things are adversarial but they are random, you might still be okay. Okay. Okay, so we have those. Right.
What's going to happen? What's going to happen is basically go straight to stock.
So demo of world assumptions, random ghost, and so which case is this? Which case is this? Random ghost, Expectimax Pacman. Which one? Random ghost, Expectimax Pacman, this one. Okay.
What's going to happen? What's going to happen is basically go straight to stock.
So this is fine. Again, what are we doing in this case? Pac-Man assumes that the ghosts are non-adversarial, they are random, which is indeed the case. Next.
So you use minimax.
So just a second, wait. What is this? Ghost is actually adversarial. Pac-Man is minimax. So what is it in this case? This is minimax game. Ghost is adversarial, is going to go after Pac-Man, and Pac-Man knows this, and it is going to try all way out to eat this pellet.
Go for the dot because you know it's going to get on top of you and you're going to die. And so you kind of lead it on a chase.
Right? So Pac-Man has a way of doing it. This is fine. Now comes the next two. Again, what is it? First, understand the situation first. Adversarial ghost, and so Pac-Man is going to assume that the ghosts are random.
It's going to come right for you, but you don't know that. Well, you're going to take a risk. And the ghost is coming right at you, but you just can't imagine it's true. You keep taking these risks. Maybe it works out or maybe it doesn't.
Okay. What happens in this case? Random ghost. So what will happen in this case? See, ghost is random, but Pac-Man is going to think that it is adversarial. Okay. So carefully look at this one.
So you run away, and what does the ghost do? It kind of does its thing. But you're scared, right? Because at any point you're like, any moment now it's going to bust out its master plan, right? Oh, random number generator. Until at some point, no.
So which case was this? Minimax, dangerous, pessimism, right? So Pac-Man assumed that the ghost is adversarial, but ghost was actually random. All right, we go. I don't really know how to play this game. Anyone? So I have no idea. Just that somewhere in the slides they will tell that the branching factor for this game is, I think, 300 or something like that. So Expectimax. Environment is an extra random agent player that moves after each min-max agent. Each node computes the appropriate combination of its children. Maybe you can better classify the games now. Environment is an extra random agent player that moves after each min-max agent. Each node computes the appropriate combination of its children. Maybe you would like to reclassify things now. Will chess come here? No. Tic-tac-toe? No. Which game might come here? See, look at here. Environment is an extra random agent player that moves after each agent. That means then environment will play. After that you are going to get your chance. सबवे सर्फर क्या होता है इसमें? वन प्लेयर है कि मल्टीप्लेयर है?
पुलिस को अगर वो कंसीडर
ओके
adversary हो गया कि वो जो practically obstacles आते थे
नो बट डज इट फिट हियर नहीं टेल मी वेयर विल लूडो गो नाउ environment is an extra random agent player that moves after each minimax agent, right? So when we are playing ludo, let's say two of us, none of us is random, so it was not Expectimax in the previous sense. In this case, so let's say you are min, I am max, but both of us are influenced by this random agent called environment, right, which is the dice that we are rolling. Make sense? Chalo. So how will the tree look like? Earlier we had replaced min with chance nodes. Now, so consider these three players. You will have these three kind of players. Okay. So I have no idea how to play this game, but let's talk a little bit about this. Okay, so B is 21. There is some game for which B is 300. So probably it's not backgammon then. 20 legal moves. So depth is huge. So sorry. At depth 2, you have so many states. As depth increases, probability of reaching a given node shrinks, but still you have first AI world champion in any game, right? So what are they just trying to say through this slide, even though we don't understand this game? See, B is 21, and even for depth 2, you have billions of states, but still AI or algorithms, they are able to correctly prune, correctly deal with it somehow, that they are able to beat human beings. Okay. So usefulness of whatever. So TD Gammon uses depth 2 search plus very good evaluation function plus reinforcement learning to become world champion level play. Okay. ज़्यादा हो रहा है क्या? चलते हैं, देखिए जहां तक चल सकते हैं. So what if the game is not zero sum or has multiple players? Generalization of minimax. How many players game? अभी आसान है चीजें, जब तक आसान है we can do. So 3 players are there, denoted by coloring. So tell me how will you propagate these terminal utilities up? What is red trying to do? Maximize its own utilities. What will blue do and what will green do? Same. Okay. So terminals have utility tuples, not just one number anymore, they are tuples, because it's not a zero sum game, it's not the same number both are looking for, they all are looking for their own utilities. Node values are also utility tuples. Node values means values here. Each player maximizes its own component. Each player maximizes its own component, not a zero sum. Okay. Can give rise to cooperation and competition dynamically.
सर बट इन द एंड हमारा जो एनवायरनमेंट एजेंट है वो तो रैंडम है, सो फिर उसको अपनी यूटिलिटी मैक्सिमाइज करने की जरूरत है.
Which environment agent in this case?
ये बट मल्टी एजेंट यूटिलिटी इसमें एक एजेंट रैंडम है, 3 प्लेयर गेम एक रैंडम होता है ना.
3 player game में why do you need, मतलब why? This is a 3 player game. जो अपन ने पहले किया इससे पहले, that part is done. So if you are linking it with this, no, this is done, this is over. Okay, now this is a different thing, multi-agent utilities, not a zero sum game. So utilities are different for every player now. I don't care what do you do, I am going to maximize my own.
तो adversaries
Can give rise to cooperation and competition dynamically. So everybody is trying to maximize their own thing. If it gives rise to cooperation, fine, competition, fine. Yes, games become complex now, right? So I won't like to take examples. For example, so I mean my bet would be 3 people playing AOE, Age of Empires, or I don't know other games, Counter Strike. हाँ यार पुराने आदमी क्या करें, right? So all right, so done. How do you bring these numbers up now? How will you propagate numbers up? This is green here. So what will green do? 166. So this thing goes up, right? Will this go up? What? So which path? Let us say which path will red like to take? Either this one or this one. Okay, but who who plays right now? Green, and green will choose which one? 166. So 166. What happens here? 612. What happens here? 517 instead of 152, and this is 525. Once you have here, give chance to blue. So blue will do what? Among this and this, so it is going to take 166. What is here? 517 and 525. Blue will take 525. यहाँ पे क्या गया था भाई? 166 and 525. Red gets 5. Okay. So what is the optimal play? This one. Questions here? प्रून कर सकते हो? I don't think so. They interact so randomly with each other, right? So there is no chance of pruning as such. I'll not get into it. Can you take? See, you can do all sort of things that you want to do, right? And for this course, we are not even going there. All we are saying is, if you have multiplayers, then you have to propagate the whole thing, because it's not a zero-sum game. They are not looking to minimize or maximize the same thing. It's not same as minimax. You do your bit. If that helps others, fine. If that puts others at disadvantage, I don't care. Okay. Utilities now. And this has always been the hardest topic for me to cover, because I am neither an economist nor a game theorist. But hopefully, what are utilities that we have been talking about until now? इकोनॉमिक्स पे कितने लोगों ने कोर्स कर रखा है? एक भी? चलो छोड़ो. So what are utilities? Why should we average utilities? Why not minimax? Maximum expected utility. Right. This is the, what is this? What is this title? Remember, एकदम शुरुआत में भी आया था ये. What is the objective of this course? Maximize expected utility. Right? So this is what we are looking for. So why are we looking to maximize expected utility? So why should we average utilities and why not minimax? Why should we average utilities and why not minimax? We have seen this before, right? Because world does not behave. So world might behave like this. So we don't want to be minimax. We want to be average utilities. If we lose once, fine. But let's say 80% of the times environment is random, 20% of the times it is adversary. We still have, because we have seen how bad, what was that? Dangerous pessimism, right? Okay. So principle of maximum expected utility. A lot of principles will come in here that are coming from research and studies in economics and game theory. Okay. So principle of maximum expected utility. A rational agent should choose action such that it maximizes its expected utility given its knowledge. So this is what a rational agent will do. What is a rational agent? अब कोई एल्गोरिथम नहीं है, पूरी थ्योरी है. What is a rational person according to you? See, in the beginning or wherever you talk about. So when you read newspaper, when you see movies, what do people say? What is AI? So which mimics human intelligence. This is probably the most common answer. But as a student of AI, what should we know? As a student of computer science. See, what do you even mean by mimicking human behavior in the first place? Second place, you mimic something that you are confident of. Human behavior we don't know. Do we understand human brain? We don't. Neuroscience is, they don't claim they are anywhere close to understanding human mind. So you can't make machines that you don't understand. So as a AI class, what is AI for us? Are you trying to make machines that think like humans? No. Are you trying to make machines that act like humans? No. Now next question is, are human beings always rational? No. But we are trying to build machines that are rational. What does it mean? Given a set of constraints, given environment, given everything, whatever is given to you, you must do the right thing. Human beings are usually rational, but they are not always. So what we are trying to build here is not exactly human beings, but so one line, we are trying to build agents that act rationally. Given a situation, they should take a rational step. So a rational agent should choose the action that maximizes its expected utility given its knowledge. What does it mean? So let's say if you are playing Ludo, what does it mean for us? If you are a rational player, what will you do? Let's say you are playing with your niece of age 6. What will you do? Will you be a perfect adversary?
Yes, sir.
Right? Choose what is rationality for you. Okay? So a rational agent, now it says should choose the action that maximizes its expected utility given its knowledge. So if you are playing with your friend, most likely what will you try to do? No, when you say maximize its expected utility, what are we trying to do as a player? I don't want to make any mistakes deliberately, right? So I should make a move which maximizes my expected utility. What is that thing in case of, let's say, chess? Probability of, I'm trying to maximize the probability of winning. Okay? So a rational agent will do this. You won't try to do this कि यार ठीक है, we are not taking care of those cases जहाँ पे कि यार ठीक है, जीत गए तो भी ठीक है, हार गए तो भी ठीक है. At every step you are trying to take those actions which maximize your expected utility. Okay? So this is important. Where do utilities come from? This is a very philosophical question. Where do utilities come from? How do we know such utilities even exist? How do we know that averaging even makes sense? What if our behavior can't be described by utilities? All these questions are there. And they are for game theorists and economics to ponder upon, or maybe philosophers. Where do utilities come from? See, again, as I said before, I don't know too much of these theories, but what are utilities? See, utility theory in a way says you can assign number to everything, right? Because unless you are able to assign numbers, I won't be able to measure how should I take my next step, right? So we don't have a choice here. We are saying we should be able to assign number to everything. वैसे तो you are winning a game of chess, no numbers here, but you want to assign that. Okay? You are winning a game of Ludo, no numbers here as such, but you want to assign that. For example, if you are thirsty, can you assign a number to it? No. Only 1 0? So you can have it of varying degrees. Okay? So assign some number to it. For example, if I assign -10 to my thirst and maybe -20 to yours, so I'm trying to say that you need water more than me right now. Okay? Now let's say somebody offers you have this -20 right now, greater than -10. Somebody offers you first glass of water. What happens to your utility now? Right? So it should change. Right? And so on. So those things are called marginal utilities. We don't go there. How do we know such utilities even exist? We don't know. We just assign. Right? Because as you said, this is our need. We are trying to build algorithms, so we need numbers to be able to compare. How do we know that averaging makes sense? वही वाली बात, world is not completely pessimist. Okay? What if our behavior can be described? What if our behavior can't be described by utilities? Then you won't be able to make systems that are good, but we should still assign utilities. What utilities to use? So 0, 40, 20, 30, that same minimax tree. If you square it, 0, 1600, 400, 900. For worst case minimax reasoning, terminal function scale doesn't matter. We just want better states to have higher evaluations, get the ordering right. We call this insensitivity to monotonic transformations. If you want to sleep, maybe this is the right class. Okay, but anyway, so what are utilities? ये बात बताओ भाई, सिंपल एकदम हिंदी, शुद्ध हिंदी में यूटिलिटीज का आइडिया समझ में आ रहा है ना? वी आर नो वे डिफाइनिंग देम, वी आर नो वे डूइंग एनीथिंग विद देम, वी आर जस्ट ट्राइंग टू सी व्हाई डू वी नीड यूटिलिटीज? Because we are designing algorithms, we need to compare things, we need to assign something is better than other thing, so we need numbers there. Okay? Now, what if utilities, what if you can't define utilities properly?
We can't treat this as
Probably you will not be able to make that system well, but you should still assign utilities because that is the only way for us to proceed. Okay, what happened in this case? Whether you use x or whether you use x square for minimax, it does not matter, right? Because I will still look for this number here, and this state, terminal state, does not change even if I square it. For average case, so for minimax, this was same. Now what happens for average case? Average here was, so if this is a chance node, average here was 20, average here is 25. So if it's a chance node, I was going here, and if it was a min-max, I was going here. The moment you square it, average is 800. Average is less than 800. So for Expectimax, it changes. Earlier I was taking this path, now I should take this one. So for average case, Expectimax reasoning, we need magnitudes to be meaningful. It's not that आपने square कर दिया तो भी fine है. Those numbers should make more sense in case of average. Which one do you assign the maximum utility? So utilities are functions from outcomes, states of the world, to real numbers that describe an agent's preferences. Describe an agent's preferences, and our agent is rational. Okay? So where do utilities come from? In a game, it may be simply plus minus. Utilities summarize the agent's goals. If you are building a system, then they are basically your goals defined by you. Any rational preferences can be summarized as a utility function. Again, this is a theorem, so we have to take it as it is. Any rational preferences can be summarized as a utility function. We hardwire utilities and let behaviors emerge. Why don't we let agents pick utilities? Why don't we prescribe behaviors? This takes us too far from what we are doing. We are assuming कि हमको कोई utilities लाके दे रहा है. Okay? That's why reinforcement learning is very hard to do. We'll come to, because उसमें आपको ये utilities actually में आप ही को assign करनी पड़ेंगी. Probabilities आप ही को assign करनी पड़ेंगी. जितने paths हैं आप ही को learn करने पड़ेंगे. So बताओ भाई अपनी यूटिलिटीज इसमें. जस्ट गिव मी दी ऑर्डर्स, नॉट नंबर्स. दिस वन, दिस इज द ऑर्डरिंग यू विल पुट मोस्ट लाइकली. एनीबडी आइसक्रीम हेटर्स हियर? नो. चलो नेक्स्ट. सो नाउ गेटिंग आइसक्रीम, गेट सिंगल, गेट डबल. विच वन विल यू गो फॉर? नोट दैट दिस इज अ chance node. You get single, happy. Okay? You get double, you might lose. And you might be happy. So which one will you do? This is the personal preference of a person. Okay? इसमें कितने हैं भाई? This one मतलब क्लास से पूछ रहा हूं टू रेज योर हैंड्स, इसमें कितने लोग हैप्पी हैं? व्हाट अबाउट दिस वन? But then you should have asked me one question. What is that? What is the probability of this one, right? If it is average, yeah, 50-50 B, I think it's okay. Huh? 0.9? Oh. Okay. Preferences. An agent must have preferences among, so price A, B, etc. Lotteries, situations with uncertain prices, preferences. I prefer A over B. Indifference. I don't really care whether I get A or B. Price. Lottery with probability P, you get A, with probability 1 minus P, you get, so scratch to win, you could win 2 scoops. Scratch to win, you could win 2 scoops. In this case you actually win 2, in this case you better luck next time. Rationality, we have talked about it. Rational preferences. Now इस पे we want some constraints on preferences, because otherwise we will have different preferences, of course. So we want some constraints on preferences before we call them rational. What is this, by the way? ये समझाओगे मेरे को? What was this symbol for? I prefer A over B. So I prefer A over B and I prefer B over C. Then I should prefer A over C. Okay? For example, an agent with intransitive preferences can be induced to give away all of its money. ये आर्गुमेंट मेरे को समझाओ. ओके? सो अगर पढ़ोगे ढंग से तो बहुत इंटरेस्टिंग है. क्लास में नहीं थे, वापिस आना चाह रहे हो, दिस इज द राइट टाइम. Axioms of transitivity. What do they say? If I prefer A over B and B over C, then I prefer A over C. For example, an agent with intransitive preferences, यानी कि ऐसा नहीं है, I prefer C over A, can be induced to give away all of its money. कैसे? First sentence पढ़ो. If B is greater than C, then an agent with C would pay say 1 cent to get B. If A greater, because it will make circles, है ना? If A greater than B, then agent with B would pay say 1 cent to get A. If C is greater than A, then an agent with A would pay 1 cent to get C. क्या चीज? क्यों? I don't get this. What we are saying is, if you have intransitive preferences, A, B and C are preferences. Preferences. I prefer A over B. Okay? So again, axioms of rationality. See, we are formalizing rationality too. क्यों? We are computer scientists. हमको mathematics चाहिए, हमको equations चाहिए, greater than, lesser than, हमको numbers चाहिए. Okay? Orderability. We need to be able to assign orders. So if I prefer A over B or B over A, then basically, or what is this? If I prefer A over B or you give me B over A, I am basically indifferent. Does this make sense? I prefer A over B or I prefer B over A. or A, I am indifferent to A or B. डिस्कस करना है इस पे कुछ, क्या बोलना है? देखो, आई प्रिफर ए ओवर बी और आई प्रिफर बी ओवर ए. डू आई रियली केयर बिटवीन? सो आई एम इंडिफरेंट टू ए एंड बी. दिस वॉज फॉर इंडिफरेंट. डोंट रियली केयर. ट्रांजिटिविटी, have we seen this before? So I prefer A over B, and this was or here, and I prefer B over C. This implies I must prefer A over C. Continuity, what is this? I prefer A over B over C. This implies there exists a P What are these three things, bhai? Prefer A over B over C. This implies there exists a number P P to A 1 minus P. ये P की बात पहले कहीं हुई है नहीं. सो लेट से situations with uncertain prices, P is assigned for outcome A, 1 minus P is assigned for outcome B. So P is for A, 1 minus P for C. ये इनडिफरेंस कहां से आ गया? हाँ, fine. So I mean I am not able to make sense of this. मतलब I am not able to understand this. Not make sense. Unless you guys can explain me. बताओ.
C और A की probability है, तभी मेरे को समीशन मत हो रहा है.
So probability of A is P. Probability of C is 1 minus P. Okay. Okay. Maybe. No, but this is indifferent. Fine, but I need to check this one. Okay. Similarly for this one, A indifferent to B, indifferent ही है ना भाई ये. Indifference, right? So I am indifferent to B. This implies there exists P for A. अब ये C कहाँ से आया इसमें? C anyone, okay? So there exists P for A, 1 minus P for C. P for B, 1 minus P for C. This still makes sense. So I think we need to understand what does this mean. ये पहले आया था, राइट? नो, सो आई थिंक एक बार अपन इस टर्म को अंडरस्टैंड करते हैं. सो लेट्स गो बैक. It was here. It was here. Right? So an agent must have preferences among prices, lotteries. Situations with uncertain prices. Okay. So situations with uncertain prices, what does this thing mean? There is probability P assigned to outcome A, probability 1 minus P assigned to outcome B. Okay. Now we are here, probability A assigned to P. So there exists a P such that probability P is assigned to A, 1 minus P is assigned to C.
सर अगर दो नोड्स थे A, C and C and B. So if A is P, then that node की जो C होगा तो 1 minus P. And similarly वो second node के लिए भी होगा. So दोनों options are indifferent to each other. उस नोड से जो ऊपर जाएगा उस नोड से जो ऊपर जाएगा they're indifferent. दोनों में से एक दूसरे को affect नहीं कर रहे वो.
This still makes sense to me. Is this problematic? This is still okay with me because probability of A is P, probability of B is P, and then there is something else as well. So I'm indifferent to B. I'm indifferent between A and B. This is fine, right? I don't understand this one. So let's say, can I say for P equal to 0.5, probability of A is 0.5, probability of C is 0.5. This means I'm indifferent to B because B must be in between. But I don't like this argument because this won't work only for just P equal to 0.5. In general, I should be able to construct a case जहाँ पे P can change, and I'm not able to think of a case जहाँ पे P will change. Because else, why put point there exists P? Should simply say for P equal to half.
But B एक differently node है ना.
Sorry?
It's a different, completely different node other than A and C.
Right?
तो B की जो probability है that won't affect A and C. So जो ऊपर जो आएगी, दो preference ऊपर आएगी they're not affecting each other.
फिर ये A greater than I prefer A over B over C, ये कैसे है?
मतलब
What you are saying makes more sense here. Is this one fine? This is okay, right? Why is this fine? If probability assigned to A is more than the probability assigned to the other A, right? So basically I prefer A over B if the chances that I get price A are more than the chances that I get price. So right, so if there are two things and एक में probability of A ज़्यादा है than compared to दूसरा, right? Then I prefer this. This is fine. I don't get this one. क्या चीज? No, see, there are outcomes, there are ways of doing things such that probability P greater than Q implies probability of A so
we don't know that P और 1 minus P में से बड़ा होगा.
देखो, if P is greater than Q ना, that alone is sufficient to enforce this.
But how does that signify that
You are preferring this whole thing over this whole thing. Folks, इस पे कुछ go and look at the Berkeley lectures and we'll come back to this maybe. Okay? अभी नहीं. By the way, these are okay. These are axioms, so we'll not be able to prove them. They are just as it is. Rationality confirmed. I think it is enough for today.